Hello everyone, my name is Francisco J. Rodriguez Lera. Today I'm here to present for the thesis 2020 our presentation about traceability and accountability in autonomous agents. This work is part of accountability in service robot research. That is a work in progress from Grupo Robótica Universidad de León, Brilliant Robotics Lab from Universidad Rey Juan Carlos, and Skyle, the high performance computing in Castilla y León. This presentation is going to be divided in four classical steps: introduction, proposal, demo, and conclusions and further work. So first I'm going to make a brief presentation. Robot industry is hot. We can see a lot of robots everywhere, not only in industry. Nowadays we can find different robots like Pepper in malls, or like now in different therapies in schools or daycare centers. So the ability to understand why a particular robot behavior was triggered is a cornerstone. It's quite important when we want to trace why the robot is making that task. Why? Because usually the robots are working smoothly and there is no problem behind. But in the moment that we are moving from industry to real world scenarios, there are several variables in this scenario that could be failing. For instance, interacting with a human. So we need to be able to infer which component, which software component, or which hardware component was able to generate that behavior. So the research question in our research is how do we trace a particular robot behavior since it was triggered at software level to its action in the robot? Of course, also, we have another sub-questions that are current mechanisms able to update, recognize, and control unexpected robot behaviors using logging sources of information. And this is quite straightforward to see when we present it graphically. In this case, what we have is a physical layer that is in this part, and we have the control layer. Of course, we have the knowledge layer. All these layers are working together to generate different robot behaviors. The point of accountability is to be able to infer when, where, what, why, how, and to whom this robot behavior was generated. For this reason, usual approaches like sensors and actuators logs from different firmware components or low-level drivers are providing maybe too raw information to be able to infer the high-level decision that provoked that the robot behavior was generated. Okay, so for this reason, we need to check in different points where or what is happening in order to be able to say why that behavior was generated. So our proposal divides to face this problem in three different ways. First, facing the accountable and logging data. It means the classical how we check the raw data, the logs that are dumped in files, are dumped in the screen. Then, how we are going to make accountable events. It means the results of different algorithms and plans that are happening in the robot, how we are able to map this information. And finally, how we use cognitive information and other mechanisms at high level, like such as finite state machines or planners that are generating and making decisions in the robot and provoking and triggering robot behaviors. Again, a graphical approach just to see what is happening or what we want to mean with our explanation. It means that when we are generating a robot behavior, these are one behavior, two behaviors, three behaviors, the fourth behavior. Sorry. So these behaviors are concatenated, of course. It means that the robot is doing one task, another task, so on. But what we have here is a set of events that are triggered after different component layers were obtaining different information from actuators and sensors. If we just focus at low level, the classical approach of logging, we have the classical debug way. It means a lot of raw information that are dumped in files. Of course, from our previous work, of how to improve ROS, Robot Operating System logs, to simplify the process of reading debug logs, we can see that it's necessary to reduce these logs in order to be able to infer what is happening behind when the robot behavior is generated. And finally, we have the events that when we put 1 or 2 or 3 together are able to trigger a behavior. In the paper, you will find a formalization of this approach in order to explain why an event is happening, why a behavior is happening, what is the relation between them, and also what we call the perfect mapping. It means if there is a perfect match between all the software components at the robot behavior, or just the correct mapping. Okay, but it means that we have most of the components, but we are not able to say in which moment it happens. For instance, it could be related with a black box AI solution integrated in a robotics approach. In order to explain everything, we are going to make a brief demo. The demo is just presented in this YouTube video. It's presented, and we can see the 3 layers. We have the classical robot. We have a robot with operative system, middleware, different applications, robot skills, and the control. After that, what we are going to be able to do is just to make different robot behaviors. In this way, what we want to do is just search for a ball, search for a yellow net, or search for a blue net. Why? Because we are just deploying the Turtlebot robot in a field, in a football field, a soccer field, sorry, and it's going to search for one object, another object, or another object. So we saw there how the robot is moving. When we go for debug information, just for ROS logs, we will see that it's impossible to trace everything what is happening in the robot. We have a lot of information, and this big amount of information does not allow us to evaluate what is happening. If we just move for adapted logs, it means just punctual logs, we will see that we are able to trace some components, and we are going to obtain some information of what is happening, what is seen, and we can trace what is the robot behavior and what is happening here. Of course, to trace this low-level information is quite difficult and complex and boring, of course. Then when we jump to accountable events, what we are going to see is that we just develop a machine that is a node that is giving us information about what is happening using conceptual graphs. And finally, what we have also in our system is a mechanism to use off-the-shelf solutions, like in this case, that is a tool called vcode, to present the high-level information. This is a finite state machine, and what we are doing here is just to check what are we doing now. It's just checking for the blue net, yellow net, or the ball. But the point here is to mix both of them, or depending on who is auditing our solution, just take into account one of them. For instance, here what we are seeing is that the layer robot is our robot. It wants to see the ball, or now is seeing the ball, how it's changing along the time. What we can see here in our solution based on conceptual graphs is that we are providing much more better information than the classical finite state machines approach. Of course, trying to trace the same behavior using just the log level is not as easy as we can see in the graphical approach. So this was our presentation. This article presents an accountability model based on these 3 processes: the ROS logging, the events layer, and the behaviors layers at high level. And our further work is just focused in how we are going to move this to ROS 2, is release the software, and also to evaluate the impact of applying different cybersecurity techniques in the system. Just for instance, for encryption and tampering in current social robots. So that's all. Thank you for attending this presentation, and our thank you to INCIBE, Skyle, and Proyectos de Ministerio. Thank you, everyone.